okay? Because I don't know. I'm now recording, so I will record the session and then send you a link of the recording. Okay. Anyway, there is a recorded lecture from Professor Yan as well on the website. If you want to return back to it, so you will have my recording and Professor Yan recording, so you can return back to them. Okay. Any other requirement or any other thing you want to ask? Like Joe, Grylin, and Alex, Aiden. I have a lot of names here. And also anyone in room 203. Tracy, Maya, Charles, Henry, Jackson, Frank, Orland, Orzik. Any questions? Okay. So now we go to the next slide. This is the learning pyramids. As you see here, this representing the average student retention rates from lecturing or tutorials. As you see, the lecture, the retention from lecture itself only is less than 10%. And if you read while during the lecture or reading while I'm talking will be 10%, and the audio visual will be 20%, the demonstration 30%, and 50% when we make a discussion. So the discussion will make you at least got a retention of 50% of what I am saying. So that's why the discussion will be the best, one of the best ways to get the most benefit of the lecture. And also then 75% using the practice doing. So when you practice yourself will increase your retention about 25% more. And if you understand what you got in the lecture and try to help other students and try to explain to them, this will also give you more retention of the course up to 90%. Okay. The main thing here is to know that the discussion between us will improve your retention of what we are saying in the lecture up to 50%. So please feel free to discuss with me and stop me whenever you need. Okay. And now we have, as any courses, we have feedback of the course, and your feedback is important for us to improve the course and improve our performance. So please, uh, please, uh, please complete the feedback before the end of this course. So you will have a link or something to evaluate the course and tell us your notes or your comments about the performance of us and the course. So please feel free to raise any issue and concern or suggestion at any time. So we have two things from you. Complete the evaluation at the end of the course, and anytime when you have any comment or any issue or any concern or any suggestion to improve, at any time, please send me email and I will look at it. Okay, do you have any question? No? Okay, so now this is our first lecture today. So all the previous was just introduction, general introduction of the course and the assessment and the rules we will deal with during the course. Now this is our actual our actual first lecture of the course, which is talking about the basic concept of the finite element method, FEM. So F is finite, E is element, M is method. Okay. What are the basic concepts of the finite element course, or what we are doing in this lecture? We are doing this lecture understanding the general analysis steps of finite element method. So what are the steps of the method? How to proceed with this method? The next step is to understand the concept of nodes and elements. The finite element method is discretize any structure or any member to some nodes and elements. So in this course or in this lecture, we will understand what is meant by nodes and what is meant by elements. Nodes means joints, and elements is the member connecting the joints. So we have two main parts of the finite element method, the nodes and the elements. Okay. Also, we need in this lecture to understand what is your responsibility when you use the software, because that's why only engineer or only structure engineer use the software. Because as you know, any software can be learned by anybody, but as you are designing the structures, so you have background and skills that give you the reliability to use the software. Okay. Are you still with me? Okay. So I think there is a connection or something. Okay. Now, so in this lecture again, you will know what is your responsibility when you use the software, because as we are structural engineers, so we can judge the results analysis and can can know if these results are good or incorrect and they need to be recorrected again. Okay. And also in this lecture, we will understand the definition of a matrix. Okay. Matrix is like a representation of the properties of the elements. So as we know before here, we have elements, and the matrix is how to represent the element to the software, and this will be using matrices. Okay, the last thing is to understand the concept of singular matrix and matrix inversion. So we have a concept called singular matrix, and we also will do some mathematical calculation to get the inversion of a matrix. Okay, so this is our aims for this lecture today. And the first thing is some explanation of what is the method. So again, FEM is the finite element method, which is a computer-based procedure that can be used to analyze structures, and so on. So finite element method is computer-based procedure. So we will use computer to help us to proceed with this method, because this method is very complicated when you do it manually. So the software will help us to make it faster. Okay. The finite element method is based on the idea of building a complicated object with simple blocks. Okay, so this is the main concept of the finite element method. We have a complicated structure or have a complicated building, and we need to subdivide it to small parts to make it easier to deal with the small parts. When you deal with the small parts, it will be easier, and then after dealing with many small parts, we connect them all together to be equivalent to the original structure. So this is the main idea, is to divide or subdivide a complicated object into a small and manageable pieces. That's why it is called finite element method. Like you have big structure or big element, and we like divide it to small pieces or small elements. This small elements we call it finite element. Okay. After that, after dealing with the small elements, we put all together again to examine the entire structure. Okay. So the small pieces will make it easier to deal with, but after this, we will collect them or put them all together again to represent the actual or the entire structure. Okay, how many elements do we need and what type of elements are used? This is the questions we will answer during the lecture. Okay, because each element or each type of structure need uh, a proper number of elements to deal with the structure. Okay, so here again is a definition of the finite element method. F is finite. Finite means reduce the degrees of freedom from infinite to finite. Because as you know, any shape or any structure has infinite number of elements if it is not discretized. So the method try to get a finite number of the elements or make them a number that we can deal with. That's why it's called finite. Elements, all the calculation are made at limited number of points known as nodes. As I mentioned before, the structure is divided as elements and nodes. So we deal with the elements and we calculate the forces and the displacement at the nodes. Okay, the nodes are the main thing of our structure because they are forming the elements. And we can have elements shaped like quadrilateral or triangle or hexagon or whatever the shape between the nodes. So when you have three nodes, if you connect them together with the element, this will be a triangle element. If you have four nodes and you connect them together, this will be a quadrilateral element. If you have six or eight nodes, you will have hexagon elements. So the number of nodes you are dealing with for one element will shape the element between triangle or quadrilateral or hexagon or whatever. So depending on how we subdivide the element, the structure, the nodes will appear to us and the shape of the element will appear to us. Okay. Method is a numerical method for structure engineering or for engineering solution. Okay. So the main idea of the finite element again, in brief, is subdividing the complicated structure to a finite number of elements and nodes. These elements will take the shape between the nodes, between triangular or quadrilateral or hexagon. And this method is a numerical or computer-based method helping us to solve civil engineering problem or structural engineering problems. Okay. Do you have any question about the finite element method or the definition of finite element method? Okay, thank you. This is the finite element method in this slide is useful. This is where to or when to we need the finite element method. Finite element method is useful for problems with complicated geometries, loadings, and material properties where analytical solutions can't be obtained. As you know, any structure we can solve it manually using our calculation, like summation of forces, summation of moment, and analysis gets the shear forces, normal forces, and bending moment diagrams. But this will be for simple structure like one beam, one column, a frame. But for complicated structure like this channel or this shape, so it has complicated geometry and also will have complicated loads because maybe water running in or some vertical loads applied. So the geometry is complicated, the loading also is complicated. Also the material properties, maybe it is not from steel, pure steel or concrete also is not iso like the concrete properties are not straightforward like steel. So concrete also needs some uh, some effort, some more effort to deal with. That's why the software or the finite element method will be helpful in this type of problem. Okay. Also, the design geometry is complicated issue as the first step. and also the accuracy requirement is critical. So in some problems, if you try to deal with it manually or with hand calculation, the accuracy will not be very good. So we need to, okay, okay, sorry guys, I will speak a little bit slower. Okay, thank you, Professor Zing. Again, the finite element method is very useful for problems with complicated geometries and complicated loadings and complicated material properties. Okay, as you see in this shape, this is an example of the complicated geometry. So we cannot deal with this using a manual or hand calculations. So in these cases, the software or the finite element method will be very helpful instead of the analytical method, because the analytical method of the analytical solution will be too hard and also not very accurate. So when we need accuracy, not 100% accuracy, but at least acceptable accuracy, and with the complicated geometries, loadings, and the material properties, finite element method will be the best option for us. This photos shown some example of what we are talking about. So this example of complicated geometry. Then the software, using the software, we will try to discretize or subdivide the element to small elements. Then this is the behavior of the material we will input in the software. And this is the boundary condition, like the boundary condition means supports and so on. Using the software, the analysis will give us something like this. This sort of problems cannot be done manually because it is very complicated. Okay. Now, if we jump to the next slide, this will be our last part of the first session. So, or we can leave this after the break. Okay, just to refresh, and then after the break, we will start with this example of how to use finite element concept to get the area of a circle. Okay, so we will have rest for 8 minutes up to 11:50 was in my time. So after 8 minutes, we will be back. Okay, is it okay? Okay, guys, I'm back. So now, just to see an example of how to use the finite element method or something similar to the finite element method to calculate the area of a circle. So in finite element method, the results obtained from the finite element analysis are not exact solutions because it is very approximate approximation. So it will not be exact, but very close to the exact solution. It is a very accurate solution if a proper finite element model based on the principal analysis is used. So if your model is accurate and based on the principle of finite element model, so our solution will be accurate. So an example of this is a circle area, as you see. So if we want to calculate the area of a circle, so we can subdivide the circle to some small triangle like this. Okay. If we calculate the area of one triangle and sum all the triangle together, this will give us a very close thing to the area of a circle. Okay. Like calculate the area of one triangle and integrate for the number of triangles, so we get the whole area of the circle. Okay. And this is how we work it out. If we subdivide it to small triangles, so the area of one triangle is R. Let's see here. This is R, is the radius. Theta I is the angle of a circle. Angle of one triangle. So how much is the area of a triangle from here? If this is the radius, so this is theta I, and h is the height. So what is h first? H is the height, and h will be the diameter times the sine theta. So to get the opposite from the from R, so R will be H will be R sine theta as here. So H is the height equal to R sine theta I. Okay, so the area of one triangle is half times R times H. Okay, so R times H times half. So the area of one triangle will be R sine theta I times R times 1 divided by 2, which is half. So from this equation, area of one triangle is 0.5 R square sine theta I. Okay, so this is the area of one triangle. To get the area of a circle, area of the circle, AN, will be the integration of one area from I equal to 1 to N. Okay, so it will be 0.5 R square N sine 2 pi divided by N. From where we get 2 pi divided by N. Because this is a circle, so the total angle of a circle, or like 360 degrees, equal to 2 pi, because pi in radian representing 180. So 2 pi equal to 360 degrees. So 360 degrees equal to 2 pi. So if we divide 2 pi by number of triangle, will give us the number of theta, or the value of theta. Okay, so 0.5 R square N sine 2 pi divided by N. This is the integration of sine theta I. Okay, because N is, if it is N is 2, like the maximum number we can get is infinity. So if N is close to infinity, sine 2 pi by N will be equal to 2 by n. 2 by divided by n. So if we remove the sign from here, so we will have 0.5 r squared times n multiplied by 2 by divided by n. N will be omitted with n and 2 with 2. So the remaining will be by r squared. So the final area will be by r squared. Okay, where n is the total number of triangles. Do you want me to uh, do it myself, like write it down for you, or you can understand from the slide? If you need, I can do it again myself. Okay, I'll just share another screen. Okay, so here we have again. Okay, so here we have a. I don't know why it doesn't work. Okay, we have a of one triangle equal to r sine theta I. This is equivalent to the height of the triangle h times r times 0.5. Okay, this is the area of one triangle. Theta I equal to 2 by n. 2 by is equivalent to 360 degrees. Okay, because as you know, if this circle, so the total angle here is 360 degrees. So the number of triangle or the number of thetas will be, or theta will be the total angle 2 by divided by number of angles n. So from the first equation here, AI equal to 0.5 r square. Do you have questions?
We can't see you share PPT.
You can see? Okay. Okay, sorry guys, I'm sharing the screen, but can you see it now?
No.
No, not yet. So what you can see?
You should share again.
Because for me, oh, okay, sorry. Can you see it now?
Yeah.
Okay, sorry guys. Okay, well, repeat this again. Just let me know if you are seeing it. Okay, again, the area of a triangle is just a triangle. Is this theta I. This is our 90 degree. This is R. So this will be H. H is height of the triangle, which is R sine theta R. Okay. So area of one triangle AI will be 0.5 R times H. H is R sine theta R. So AI will be 0.5 R squared sine theta R, where theta I equal to, from the circle, you know that the total angle of circle is 360, which is equivalent to 2 pi. So theta I will be 360 divided by n, or 2 pi divided by n, where n is the number of triangles. Okay, so if we want to find the area of the total circle, an will be equivalent to the integration of, or the summation of, ai from I equal to 1 to I equal to n. Okay, so this means that we have n number of triangle times area of one triangle, which is 0.5 r squared sine theta I. Okay, if we replace sine theta I with sine 2 pi divided by n. Okay, so we will have n, sorry, let's say 0.5 n r squared sine 2 pi divided by n. As n is very number we don't know, but very close to infinity. So when it is close to infinity, sine 2 pi by n will be equivalent to 2 pi by n. So the value of sine will be, because it will be 0. If you know, if n if n like very close to infinity, so this will be almost 0. So sine theta, sine 2 pi by n will be equivalent to 2 pi by n. So if we replace this, so 0.5 n r squared times 2 pi n. So n will be omitted with n, 2 with 5 with 0.5. So the final value will be pi r squared, which is a value of the circle, the area of the circle. Okay? Can you understand this? Okay. This is how to calculate the area of a circle. I already saved this one and I will send it to you later. So hopefully you get it. Okay, this is just an example of how to use the finite element method, or how to divide shapes and get area of a circle. Okay, now next, this is the engineering application we may face in the engineering projects. First of all, we are concerned with the effects of forcing action function like loads, flow pressures, and so on systems like uplift, soil pressures, flow pressures, loads like life loads, dead loads, wind loads, earthquake loads. In several instances, the problem we address is too complicated and to be solved appropriately or satisfactorily by classical analytical methods. due to the complicated geometry, it will be very hard. So the finite element method will be used here because it depends on the discretization of the member of the structure to small elements. So this again why we use finite element method in engineering application. Okay, finite element method is probably the most widely used form of computer-based engineering analysis. So the finite element method is widely used in our field. So you need to know it and it will be important for your career. Okay, and there is a video here, so you can have a look on it about the engineering application of the finite element method. Okay, now some of the common applications we face in our engineering field include static and dynamic and thermal behavior of physical systems, like static analysis of building or house or a factory or warehouse or whatever, or dynamic analysis under seismic loads or wind loads, thermal behavior under temperature exposure. So we can do this for the whole structure or some of the elements or the components like beams, slabs, columns. And here is some of the application: mechanical, aerospace, or civil engineering. And we have structure analysis, static, dynamic, linear, or nonlinear. So this is a type of analysis. You can do it static analysis. The loads are not moving. Dynamic analysis. The loads are has a function in time. Linear is taking the only the linear behavior of material and geometry, or nonlinear taking the nonlinear or plastic behavior of the materials, thermal and fluid flows, geomechanics, and biomechanics. So our application in this course will be structure analysis, static and dynamic, linear or nonlinear, and civil engineering. Okay. Some of the examples. Here is a curved beam. Like let's say it is used in stadium or covering something very long with only a cantilever beam with a curve. So as you can see, here is the model on strand 7. And if you see here, this is the support. And the small part is what we call element. So as you can see here, the elements are very small because we have some irregularity in shape. So if you take a small one of this is a finite element. And the element in this case is quadrilateral element because it is a four sides elements and we have four nodes. Okay, so this is just an example of the applications, curved beam. A second example is a concrete framed structure. As you can see, it is 6-story building or 5-story building, has some slabs, concrete beams, concrete columns. And if you can see the arrows here, this arrow shows the lateral load or wind loads application. So this is also one of the application we can face in the using the finite element methods. And this is a beach chair. So this is a beach chair and modeled by Strand 7. And this is a picnic table. So we have table with 4 chairs and we have some vertical loads on the table itself. So this is some of the model. This also a bridge
I'm sorry.
modeled on Strand 7.
We can't see your sharing screen.
Okay. Can you see now?
Yeah.
Okay. Again, these are some examples of the beams. oh, sorry, some example of the finite element application we have curved beams like this one. So if you have this is a curved beam, maybe covering a stadium or a theater or and so on. So this is a curved beam. If you can see, it is supported here from one side. If you see here on the left side at the bottom, you can see some purple and white lines. This representing the support, which is the fixed support. And if you can see the elements, the beam is discretized to small elements, small quadrilateral elements. Quadrilateral means four side elements. So we have four side element with four nodes. Okay, so if we have four nodes and we connect them together you will have quadrilateral element. Okay, and if you can see here, the elements are a little bit smaller here because we have irregular shape at this area and stress concentration. So that's why you can see that the elements at the curve are smaller than here, because here it is almost regular, so we don't need bigger, smaller size elements, but here because it is irregular, so we need smaller size elements. Okay. A second example is frame structures. This is a reinforced concrete frame structure, consists of slabs, columns, beams, and if you can see, the white arrows here are going horizontally or applied horizontally on the building. So these are representing the wind load or earthquake loads. So we can also face this type of problems in our study in this course. And this is a beach chair modeled by Strand 7. And this is a picnic table, consisted of table and four chairs, also modeled by Strand 7. And you can see some loads here in this area. Maybe a box or something is applied or put on this table, is existing on this table, so it causes some stresses here. And this is an example of a bridge. If you can see a bridge. So if you can see, there is some like I section, two I section beams carrying the bridge, and the blue is the deck of the bridge, and these two reds are the sides of the bridge. Okay, so also we can face some bridges problem using finite element models or Strand 7. Okay, this is the same bridge if you have a look here, but this is a close view of the bridge. So again, the bridge is supported by two I-beam or T-beams here, and the blue is the deck, and the red is the side walks. Okay, and this is an example of suspension bridge. Suspension bridge has like two big bear or pylons, four pylons carrying the cables. We have two main cables, the red ones, and these two cables has some yellow suspension cables to carry the deck. So the suspension bridge mainly supported by the four pylons, the four blue pylons, and these four pylons are carrying the two main cables, and the cables are suspend like the deck is suspended to the red cables by the yellow cables. So this is a type of bridge called suspension bridge, maybe also studied or investigated by Strand 7. And this is an example of a bus shelter in a bus station, or like where people can wait for the buses. So you have here the the ceiling or the cover of the shelter, and we have two sides, and we have the back. All these are plates to to resist the wind or to reduce the wind on the people waiting. And also, if you can see here, In this page, the second figure, the second image, you will see the support. So we have two columns, two red columns supported at the end here. So this is also an example of shelter. Also, some people like computer simulation for the 9th of September 2011 of September 11, sorry, 21, 2001. You know the attack in 11th of September 2001. Some of the engineer modeled this attack. You can see the video using this link. Maybe I can show you the video. Just a second. I think you can see the video now. Okay.
This video illustrates the efforts of a team of visualization and civil engineering researchers using a high-fidelity visualization of the September 11, 2001 attack on the World Trade Center. The visualization had to be eloquent to the non-expert user. The simulation was placed into context by modeling and importing the buildings of the WTC Plaza, shown here in color, into a Google Earth model of Lower Manhattan. A finite element analysis simulation of the impact between the Boeing 767 and the top 20 floors of the North Tower was computed using a state-of-the-art simulation code. Then, the simulation results were imported into a state-of-the-art animation system where the visualization was produced. The simulation tracked the impact over 3/4 of a second real time. This sequence is 13 times slower than real time. All the animated geometry seen here was created automatically from the simulation output data.
Okay, guys, so now we have had a look on the video, and this video is structural engineers. Sorry, Professor Zink. Oh, yeah, okay, thank you. So the structural engineers need to know from a scientific point of view what happens to the building during the attack and how to prevent the future events like this. And the search for answer continues with help of state-of-art animated visualization created by researcher at Purdue University, as you see in the video. So this visualization will take into consideration that the height of the planes and the foil explosions and all the fire and fire. So what do you think about this? What do you think about this simulation? So I think it is very complicated, but uh, a very good one. Do you have any comment on this? Okay, so now we jump to the next slide. This is also another example of the simulation. So if IU bridge collapse, you can see the video, and also there is essay about the collapse if you want to read it. So in this bridge, the designer overestimates the strength of a critical section and they underestimate the load on the same section. So there is a design error from the engineers. They underestimate the loads applied on the section and also overestimate the strength of the material at this point. So become a weak point from strength and also from loading. So the load were very high and also the strengths were very low. So this caused the collapse. So the cracking observed in the bridge before collapse and was consistent with the design error. So when they checked the design, the cracks was at the same point of the design error. Okay, so that's why in our career you have to make sure that your design is correct, and when you use any software, you have to make sure that the results are correct because it may cause catastrophe like this. Okay, so next, this is a brief history of the finite element method, how it is developed. It was developed in 1943 by Courant. Variation method was called the variation method. Then in 1956, Turner and Clough and Martin and Tobb developed the stiffness method. In 1960, Clough developed the finite element method or improved it to make it finite element method for plane problems. In 1970s, applications on mainframe computer. So if you want to, there is a link here, you can read more about mainframe computer because the finite element method has its biggest improvement using the computer. So at this stage, mainframe computer was developed. In 1980s, microcomputers start to appear and both processors. So with also the technology we got in computers, the finite element method improved. In 1990s, the analysis of large structure system start to appear. Okay, in these two links, you can have some more reading about the mainframe computer and analysis of large structure system. And this is some photos to show you the mainframe computer before. So now we have small laptops and small computers, but before the computer was mostly filling a big rooms. So we have much development in this field. And this is also an example of large structure system, which started in 1990s. As you can see here, this like a model, a whole model of a structure using software called Autodesk Robot. So the whole structure is modeled at once, and this contour showing the stresses on the elements. This is also a model of a bridge or something like a cover of something with two holes. So these models are sort of large structural systems that we can model nowadays. Now we start the finite element analysis, and what is the steps of the finite element analysis? So the first step of the finite element analysis is to know what is the type of analysis we are doing. As you can see here, we have this is a screenshot from the software. You have solver. This is the type of analysis we are doing. So we have linear static, linear buckling, node inference, nonlinear static, quasi-static, and so on. So these are the type of analysis we see. That, as we mentioned before, we have a static or dynamic, linear or nonlinear, buckling, thermal. So we have a lot of types of analysis. Many programs provide modulus for different type of analysis, as the screenshot you see here on the right. As example, static or dynamic analysis. Okay, so this is first step of the analysis is to know or to define what analysis you want to do, like linear or nonlinear, static or dynamic. The second step is to define the type or types of elements to be used in the analysis. As we mentioned before, we have elements, so we need to know which element is the best option to model our structure. So the typical elements type in software or infinite element method are truss elements, which only carry axial loads, beam elements, which can carry axial or shear or moment, plane stress or plane strain element, which are blades but has some constraints, plate, which is like a slab or and so on, shell element, like slab but also has some restriction. So there is a difference between shell and like they are quite similar but small difference between them. So the second step of analysis of finite element analysis is to know or to define the type of elements you are using for each member. As you can see here, this is solid element. Solid elements like 3D elements. It has width or length and height. For shell elements, it also has width and length, but the thickness is small compared to the width and length. Beam element is like a line element. It can be rectangular or I-beam or T-section. Rigid elements are elements like has width and length, and we ignore the thickness. Membrane elements quite similar to rigid elements, but it has some can have some curvature. Infinite elements is elements that is disclosed, that it is open from one side. Connector or springs, so connector or springs that show that it has some elasticity in movement. Like if you see this spring, so it can be compressed. Truss elements is like line element, like the beam element, but can only carry axial force in the direction of the beam. Okay, so this is the second step of finite element, which is to define what is the element you are using for structure analysis. What is the type of elements you are using for finite element analysis? Now, the next step is to define the location of each node in global coordinate. As you can see here, this is the like meshing or the discretization of structure or a part of structure. So we need to define the location of each node in global coordinate or global coordinate system. Like each node should have some coordinates. The next step is to connect the element at the node to form an approximate system for the whole structure. So after we know the nodes, the members between the nodes are the elements, and then we need to connect all the elements together to form the whole structure. Okay. The next step is to define the boundary condition of the problem. To define the boundary condition of the problem. Okay, define the boundary condition. The boundary condition are the supports of the structure we have. The next step is to apply the loads on the structure. A wide variety of loading conditions can be applied to a structure, like vertical loads, horizontal loads, thermal loads, air pressures, water pressures or fluid pressures, thermal heat transfer, and so on. The next step is to assign the material properties. Again, more than one material property may be used in a finite element model. In some models, like concrete, reinforced concrete slab, we have two materials. We have concrete and steel. So we have to define the material properties for all members. The next step is to execute the input file to produce the result, like run the model or solve the model. So after all the other steps, the previous step, now we run the model to get the result. The last step is to process the result and make sure that the results are correct and logic. This will be using your engineering skills and background to judge if the results are correct or not. So again, a brief of the analysis of finite element analysis. We have to define the problem. This is a pre-processing, defining the geometry, specifying the element type or defining the element type, defining material properties, creating meshes and nodes, which is the elements and the nodes of the structure or of the elements we have. Okay. And the next step is the solution or the processing. We assign loads, assign constraints, which is the restraints or the supports, and then solving the problem. Okay, the post processing is viewing the results, lists of node displacement, deflection plots, stress control diagrams, animations. So all this is to like show the results and judge the result if it is correct or need modification. Okay. So this is are the steps of analysis, the finite element analysis. Okay, can we have a rest now for 10 minutes or 15 minutes? Okay, we'll have rest up to 12:40, 12:50 on my time. So just 15 minutes and we'll be back. Okay, guys, are you back? Can you hear me? Okay, thank you, Gilbert. Okay, now our last slide was the steps of finite element analysis, and I will go through them again. So we have pre-processor, solution, and post-processor steps. So for the pre-processor steps, defining the problem and the type of analysis we are doing, defining the geometry, specifying the element type like truss element, beam element, shell, and so on, defining the material properties, and any model can have more than one material properties. For example, the reinforced concrete structures has concrete and steel, and then creating meshes and nodes, which is discretization of the big structure of the whole model to small elements or smaller elements. Then the solution containing the assigning of loads. We have many types of loads like life load, dead load, wind load, earthquake load, thermal loads, air pressure, water pressure, and so on. Assigning the constraint, which is supports, or because any structure should have constraint, otherwise it will keep moving. So it needs to be constrained at some point. And then solving or running the model. Then the post processing part is to view the results, check if the results are logic, and list the nodal displacement, deflection, plots, and stress strain curves, strain stress controls. An example of a stress control is the the image to the right, and animation. So also Strand 7 or any most of the finite element software can run animation of the structure after results. Then the next step is definition of elements and nodes, or just explanation of them. The finite element resemble fragments of the structure. So the meaning of finite element is to again to subdivide the big structure or the whole structure to small elements that we can deal with, and the nodes are the connection between these elements because all the elements are connected at the nodes. Okay, so the nodes will be the connector of the elements, and also when you apply loading or apply boundary conditions or constraints, they will be applied at the nodes. So all our calculations depend on the nodes. All elements that share node have same displacement component at that node because if we have two elements or two members are connected at one node, the node has only one displacement. So the two elements will have same displacement. This is the idea of the connection between the elements at the nodes. Okay, and if you see here, this three example of structures we have, the one here is truss, this one is frame, and this one is deep beam. If you can see for truss, you can easily understand what's mean by nodes because the members are connected at nodes, and each member is a truss member. For the frame, we have also columns, one column, two column, and beam. So we have also elements and nodes. But for deep beam, because it is one element, so it need to be discretized or subdivided to small element. As you can see, this is small rectangular element, and all this rectangular element together can form the whole structure. So for frame and truss structures, elements are more or less natural. So you already know where is the nodes and where is the elements. But for elastic continuum like the deep beam, this example, the one here at the lower side. So deep beam or blade shell structure, the natural subdivision does not exist because if you represent it as one line, it will be like this small beam. So it cannot be represented as one line or one element. So we have to artificially subdivide the continuum into a number of elements or a number of finite elements. So this is the basic idea about elements and nodes. Okay, at sometimes you need to add some additional load, not only the natural nodes. As you can see here, if this is a beam, so it is a simple beam, so we can put one node at the end, the start here, and one node at the end here at number 6. But sometimes you need to calculate the deflection or stresses at 2 and 3 and 4 and 5. Or you have some loads at 2 or 3 or 4 and 5. So at some cases, when we require results at more location or at location in between the member ends, we sometimes need to add nodes. So instead of representing this beam as one element, we divide it to 1, 2, 3, 4, 5 elements and using 6 nodes. Okay. And when you have something like this will be more accurate. When you subdivide the element to more members, the member to more elements, this will be more accurate for our result. And sometimes when the member is not prismatic, as you can see here, it is curved shape. So that's why you need to subdivide the element to 5 elements or 6 elements and so on. For this type of structure, like curved structure, when you subdivide the element to more elements, the member to more elements, it will be more accurate. So like for this one, we subdivide it to 5 elements. If I subdivide it to 10 elements, this will make the solution more accurate. This is an example of additional nodes. So sometimes we need additional nodes if we need results at other location or if the members are not prismatic. The artificial elements, this is the one we are talking about in continuum or deep beams or shells and so on. So these artificial elements are the finite elements. This is the basic concept of our method. They can be triangular or rectangular, but rectangular is not very accurate, so we can, instead of rectangular, we call it quadrilateral. So quadrilateral, any shape has 4 sides. It can be rectangular or square or any other irregular 4-side shape. Okay, but for this two shapes, we have these elements subdivided to triangular elements. As you can see, all of them are equal in size. For this deep beam, we have subdivided this beam to some rectangular elements. This is an example of a dam or a retaining wall. This is an example, B is an example of deep beam. Both of them has a massive size or a big size, so they cannot be represented as one line or one element. So we subdivide them to artificial or finite elements. Okay. The method means that we can deal with a one element, small element like this, and we will repeat this for all elements. So if we know one, so we can know all of them, and then the finite element method rule is to collect all the data from all the nodes and like reassemble them together to create the structure. Okay. Superficially, it appears that a finite element method can be reduced by sewing the actual structure apart and then bringing it back together at nodes. So we